Hi everybody. This will be the third analysis on FT001 where all engines run on the same operating condition and develop the same fault. Today we will focus on time series analysis to forecast when the engines are due to for maintenance. In our previous lessons we assumed that remaining useful life of the engines to decline linearly and improve our baseline regression model significantly. We first introduce clipping to the real values and then utilize support vector regression, achieving a substantial improvement. However, predicting maintenance needs accurately requires us to consider the temporal dependencies in the data, which is where time series analysis comes into play. And what we will do, we will start by importing necessary libraries, reading the data and inspecting it, and we will create lagged versions of our sensor data to capture temporal dependencies. And it is important to ensure our time series data is stationary. We will use augmented decay failure tests for this purpose and apply differencing as needed. And we will build a regression model with lagged variables and evaluate its performance. We'll use metrics like RMSE and R-squared to measure how well our model predicts the REL. Finally, we will optimize the number of lags and handle multi-call linearity issues to further improve our model's performance. And let's switch to our code. Here we import libraries. Here we read our data, and we have a function here at remaining useful life, you know that, and you know that output. Let's start from that part, our fourth code blocks. What happens here? Drop sensors is a list of sensor columns that have been deemed unnecessary based on prior analysis or exploratory data analysis, and drop label combines static names and drop sensors. This gives us a list of columns that we want to remove from our dataset, and xtrain and xtest interim are the resulting training and test sets respectively after dropping the columns specified in drop labels. And let's look at this. What is interim? The term interim is used here to denote that the xtest interim dataset is an intermediate version of the test dataset. It has had some pre-processing done, but it may still need further pre-processing steps before it's fully ready for modeling. And now we will talk about the lagged variables. Lagged variables are essentially past values of variable that we include as additional features in our dataset. And in the context of time series analysis, lagged variables help capture the temporal dependencies and patterns in the data. And why we will use lagged variables? The time series data is sequential, and the value at a particular time point is often influenced by its past values. Lagged variables helps us incorporate this sequential dependency into our model, and including lagged variables can improve the model's ability to predict future values as it provides more context. And creating lagged variables is a form of feature engineering where we derive new features from the existing ones, and these can sometimes reveal hidden patterns and improve model performance. And I think it's okay, and let's look at our fifth line, and let's talk about them. What we can say here, NP random seed and 42, it ensures that the random numbers generated are the same every time the code is run, and this is useful for reproducibility, you know that. And toydf, what is this? This line creates a data frame with a single column named value containing 5 random numbers between 0 and 1. And what happens to another lines here, value like 1 and value like 2. It creates a new column value like one which contains the values of the value column shifted down by one, and here shift 2, it creates another new column value like 2 which contains the values of the value column shifted down by 2 rows, and display part. It outputs the data frame so we can see the effect of creating the like variables. And let's look at this output. The value column contains the original random values, and value like one column contains the values of the value column shifted by down by one row, and the first row is none here because there is no previous value to shift into this position, and value like 2 column contains the values of the value column shifted down by 2 rows. The first 2 rows are none for the same reason, and here 0 point let's say 37, and again here 0.37, and here 0.37, it's liked, I mean, and again here 0.95. Let's look at this 0.95, and again, and same part here, and again we'll continue like that. And okay, let's switch. I hope you understand what is liked and what happens here, and let's look at the our sixth part. Switch. Okay, let's talk about this. Remaining sensors here. This selects all columns in X-train that are not part of the index names or remaining useful life. Essentially, these are the sensor columns we want to create liked versions of. And leg 1 here. This creates a list of new column names for the liked variables, appending leg 1 to each of the remaining sensor column names. And X-train leg 1, what happens here? This creates liked variables for each of the remaining sensors by shifting the values down by one row within each group of unit number. And X-train drop name, what is here? This removes any rows that contain non-values which are introduced by the shift operation. And X-test interim here, similar to training set, this creates liked variables for the test set and removes rows with non-values. And target part here, X-train pub. This separates the target variable from the training data. The pub method removes the remaining useful life column from X-train and assign it to Y-train. And here X-test, what happens here? This selects the last row for each unit number in the test set, ensuring that we have one final observation per unit for prediction purposes. And reset index method is used to reset the index of the data frame. And you know that part. We have a function for evaluation, and here we will fit and create linear regression model. And let's talk about the train and test sets. You can see the RMSE and R squared score values, and I think we can switch to other parts. Here we have a new function add liked variables, and what happens here? This function adds liked variables to the dataset for a specified number of likes. And what are the parameters? df input, the input data frame, number of likes, here the number of liked variables to add, and columns here, the columns for which to create liked variables, and df input copy. This ensures that the original data frame is not modified. And we have a loop here. What happens here? It creates new column names for the liked variables and use the shift method to create liked variables grouped by unit number. And drop NA, it remove rows with any non-values which result from the shift operation and return. And what we can say at specific legs, let's look at this part. This function adds leg variables to the dataset for specific legs provided in a list, and parameters def input list of legs. This is a list specifying which legs to add, and columns, the column for which to create leg. And again, def input copy, and again we have a loop. Create new column names for the leg variables and use the shift method to create leg variables grouped by unit number, and again drop NA here. Remove rows with any non-values which result from the shift operation. And let's look at our another part and talk about this. What happens here? What is at floor? This code is testing for stationary in the time series data using the augmented decay filler or ADF test. And stationary is important for time series analysis, as many models assume that the statistical properties of the series do not change over time. And let's look at this first line. This imports the add-fuller function from the stats models library which performs the ADF test. And test sets line. What happens here? Here we are selecting the sensors S7 data for the engine with unit number equal to 1 from the training set, and this isolates the time series data for a single sensor and single engine. And ADF p-value used like and ops critical values. What are they? ADF, the test statistics, p-value, the p-value of the test, and used like the number of legs used in the test, and it is the number of observations, and here the critical values for the test statistics at different significance levels. And what is this? This is the maximized information criterion if auto-lag is not none, and printing the parts. And let's look at our outputs and talk about them. First, ADF test statistics, I mean ADF here, second line. This test statistic is negative, which typically indicates some level of stationary, but the degree of stationary depends on how negative it is. And p-value, the p-value is 0.17, let's say, which is greater than 0.05, and this means that we fail to sorry, reject the null hypothesis of the ADF test, which states that the time series is non-stationary, and significant false since the value greater than 0.05, the result is not statistically significant, meaning the time series is considered non-stationary. And let's look at another part and talk about them. Here, 12th block. This part of code continues to check for stationary in the time series data using the augmented decay filler test, but it first applies differencing to the data. Differencing is a common method to remove trends and make the data stationary. And here time series, the diff1 function calculates the difference between consecutive data points, essentially transforming the time series to representing changes rather than absolute values. And drop NA here. This function removes any resulting NA, I mean non-values to appear due to the differencing. And here ADF p-value used like an ops again. You know that part. The add-fuller function is applied to again to different time series. The parameters and returned values are the same as before. and again print parts. And let's look at our new output here. ADF minus 14.82. The test statistic is significantly more negative than before, indicating a stronger presence of stationary in the different time series. And here p-value, the p-value is now extremely small, which allows us to reject the null hypothesis of the ADF test. This means that we can confidently say the difference time series is stationary and significant true, since the p-value is much less than 0.05. The result is statistically significant, meaning the time series is now considered stationary after differencing. And let's look at our another function, find max diff, and secondly max stationary. What happens here? And let's talk about it. First, we will focus on that. To determine the minimum number of differences required to make a time series stationary, here max diff equals 0 for initialize variables and do equal true. And here EDF test, first EDF test. Conduct the augmented decay follower test to check for stationary. If the p-value is below 0.05, the series is already stationary and no differencing is needed. And let's look at the while part here. It apply differencing iteratively until the series become stationary, and return max diff. Return the number of differences applied to make the series stationary. And what we can say, function make stationary here to make all specified columns in a data frame stationary by applying the minimum number of differences required for each column. And df input copy, and we have a for each unit and column, find the maximum number of differences required to make the column stationary using the find max diff function, and apply the required differencing to the column, and drop NA here, and return part, return the modified data frame is with the stationary columns. And let's look at the intermediate DF parts and talk about them. Here, let's stop here. What happens here? Intermediate DF and train drop levels x1. This line drops the columns specified in drop labels from the train data frame, and the drop labels typically include settings and sensor columns that were deemed unnecessary or redundant based on prior exploratory data analysis. And these steps helps in reducing the dataset to only those columns that are most relevant for future analysis. And here, second line, this line calls the make station function on the intermediate DF data frame, which applies the differencing process to make the specified remaining sensors columns stationary. And stationary is an important assumption in many time series forecasting model, as it ensures that the statistical properties of the time series do not change over time. And let's inspect the data, and let's look at the output. Unit number, the identifier for each engine unit, and time cycles, the number of cycles the engine has run, and sensors, the sensor readings for various sensors after making them stationary, and RVL, the remaining useful life of the engine, which decreases as the engine operates. And I think it's okay. And let's look at our linear regression part. And here, model creation. First, these lines initialize a linear regression model with LM using the linear regression class from the scikit-learn library. And fit here, the fit method is then called on the LM object, which trains the model using the stationary sensor data as the input features, and the remaining useful life as a target variable. And this step involves finding the best fitting line that minimizes the error between the predicted and actual remaining useful life values. And whitehead tree, the predict method is used to make predictions on the training data, and intermediate remaining sensors using the fitted linear regression model. At evaluation, the evaluate function is called to access the performance of the model. It takes the actual RUL values, the predicted RUL values as inputs. This function calculates the root mean squared error and R squared value. And let's look at the R values here. First, RMSE. The RMSE value is approximately 51.63, and RMSE measures the average magnitude of the errors between the predicted and actual values. A lower RMSE indicates better model performance, and in this case, an RMSE of like that suggests that the model's predictions are on average about 51.63 units away from the actual RUL values. Another hand, R squared, the R squared value is approximately 0.43, and R squared measures the proportion of the variance in the dependent variable that is predictable from the independent variables, and an R squared value closer to 1 indicates a better fit, and here our value suggests that here 43.4% of the variance in the RUL can be explained by the model, and this is a moderate fit, indicating there is a significant portion of the variance not captured by the model. And the RMSE for this model has increased compared to the previous models where the data was not made stationary, and this increase can be explained by the fact that the data are now stationary and no longer has a trend, making it harder to fit a regression line. And the next step to improve performance is to add liked variables. These variables capture the relationship between changes in sensor values over time, providing more information to the model. And by incorporating these liked variables, the model will better understand the temporal dynamics of the data, potentially leading to improved performance. And I hope you understand. And let's look at our another parts and and what happens here. First, we will talk about the Akaike information criterion. What is this? It is a measure used to compare the relative quality of statistical models for a given dataset. It balances the model fit with the complexity of the model to prevent overfitting. And here is the formula from bulletin.com website. Here, K is the number of estimated parameters in the model, and L here is the maximum value of the likelihood function for the model, and a lower Akaike information criterion, AIC, or value indicates a better model, and AIC takes into account both the goodness of fit and the simplicity of the model. And by comparing the AIC values of different models, you can choose the model that best balances fit and complexity. And again, let's look at our code. First, it imports the StatModels library, which provides classes and functions for statistical models. And here it creates an empty data frame to store the root mean squared error and AIC and Bayesian information criterion and BIC here. And number of likes here sets the number of liked variables to consider. In this case, up to 30 likes are considered. And we have a for loop. What happens here? Let's look at this part. It iterates over the change from 0 to number of legs, and for each iteration it creates liked variables for the sensors in the dataset, and it drops the index columns from the training data, and it separates the target variable from the features and model and result. It creates an ordinary less squares or OLS regression model using the training data, and adds a constant term to the model to account for the intercept, and it fits the model to the data and stores the result in the result. And matrix, what happens here? It calculates the RMSE, AIC, and BIC values for the fitted model, and appends these values to the matrix data frame, and display matrix. It displays the matrix data frame containing the RMSE, AIC, and BIC values for models with different number of light variables. And we have a list here for RMSE, AIC, BIC. What happens here? Uh, Measures the average magnitude of the errors between the predicted and actual values, RMSE, and lower RMSE indicates better model performance. And secondly, Akaike information criterion, it used to compare models and select the best one considering both fit and complexity, and lower Akaike information criterion indicates a better model. And here Bayesian information criterion, similar to archaic information criterion, but with a stronger penalty for models with more parameters, and lower Bayesian information criterion indicates a better model. And I hope you understand. And let's switch. Here we will plot our AIC rate of change, and x-axis is number of legs, and let's talk about this. From the graph we observe, let me switch. Okay, it's a steep decline in AIC initially as we increase the number of legs, and this indicates that adding leg variable significantly improves the model initially, and around here 14 legs the improvement in AIC starts to plateau, meaning that adding more legs beyond this point does not substantially enhance the model's performance, and this plateau suggests that the balance between model complexity and quality is reached at around 14 legs. At red dot, I hope you can see here, the red dot on the graph marks the point where is the plateau starts, indicating that using around 14 legs is optimal. Beyond this point, the increase in complexity does not justify the marginal gains in model quality, and thus the graph suggests that the optimal number of legs to use in the model is around 14, balancing between adding complexity and achieving model improvement, and this helps in avoiding overfitting while still capturing the necessary patterns in the data for accurate predictions. And what we can say another, let me switch, and what happens here, talk about this part here. What is this variance inflation factor? The variance inflation factor function from state models is important, and at liked variables, the function at liked variables is used to add 14 liked variables to the intermediate DF data frame for the remaining sensor columns, and drop out the index columns are dropped from xtrain, and calculate variance inflation factor. The variance inflation factor for each feature in the xtrain is calculated using a dictionary comprehension, and the variance inflation factor values are rounded to two decimal places and stored in a dictionary views here. And what we can say another, and again display parts, and it's a long list, and you can interpret, but now I will talk about them. And let me see which one. Okay, let's stop here. The various inflation values for many liked features are significantly higher than 5, which suggests that the model suffers from multi-collinearity. This can lead to unstable coefficient estimates and unreliable statistical inferences. And the high multi-collinearity can affect the stability and interpretation of the model coefficients. It suggests that the model might not generalize well to new data, and the estimates of the regression coefficients may be sensitive to small changes in the model. And to address this issue, the next suggests applying to scaling transformation to reduce multi-collinearity, and scaling can help to normalize the data, potentially reducing our variance uh, inflation factor and values, and improving the model's performance. And I hope you understand. And let's switch to our scalar part. Here, this imports the SunScale class from scikit-learn pre-processing, which will be used to standardize the features by removing the mean and scaling the unit variance. And dropping part, these lines, I mean second line, removes the specified columns from the trained dataset. And you know that scalar part, it initializes scalar and computes the mean and standard deviation for scaling. And finally, intermediate DF remaining sensors here. It applies the scaling transformation to the specified sensor columns. And here, what happens here? This applies a previously defined make stationary function to ensure the data is stationary, and extrain at liked variables and extrain drop. It creates liked variables for the sensors up to 14 legs, and it removes index columns which are not needed for training. And WIF's variance inflation factor. The WIF values are calculated for each feature in the extrained data frame, and the WIF values are then stored in a dictionary with the corresponding column names are displayed. And again, we have an output. Let me switch. Let's stop here. Most of the WIF values are below 5, indicating that multi-collinearity is not a severe issue for these variables. And this means that these variables are not highly correlated with each other, which is desirable. And there are still a few WIF values slightly above 5. And this might indicate potential multi-collinearity issues, but given that most values are below the threshold, this can be considered an acceptable level of multi-collinearity. And the reduction in WIF values after scaling indicates that standardizing the features significantly reduces multi-collinearity, making the model more reliable and stable. And let's look at our another visual here. This plot takes summarize process and results of determining of the optimal number of legs to include in our time series model after scaling the features, and x-axis number of legs here. This axis represents the number of leg variables added to a model, and again this axis shows the change in the Akaiki information criterion as the number of legs increases. Our AIC generally indicates a better model fit, and initially adding legs significantly improves the model quality, as evidenced by the steep drop in AIC. And the plot shows at flattening around here 9 lakhs. This indicates that adding more than 9 lakhs does not significantly improve the model's performance, and thus the trade-off between model complexity and quality is balanced at this point. And after applying scaling, the optimal number of lakhs has shifted from 14 to 9. This suggests that the scaling process has affected the data in a way that fewer lakhs are needed to achieve the best model performance. And let's look at the our code part and what happens here and talk about this. Both the training and testing datasets have unwanted columns removed using drop labels. Here you can see, and scaling part with scalar transform. The remaining sensor data in the training set is scaled using standard scaler to standardize the features. And stationary part here, the scaled data is then made stationary using the make station function. And like variables here, like variables are added to the data using add like variables to include the information from previous time steps, and adding constant terms here with sm. A constant term is added to dataset for the regression model, and extract target variables here. The RUL column is popped from the training data to be used as the target variable, and again here model a linear regression model is created using sm.ols and fitted to the training data, and ytraining values here clipped at 125 to handle outliers, and here y head train and y head model fitted plot part. Sorry. The model makes predictions on both the training and testing dataset. The value function is used to calculate RMSE and R score for both training and testing predictions. And let's look at the results. The model achieves an RMSE of 21.14 on the test set, which indicates here how well the model can predict the remaining useful life of the engines. While this is a good result, there might still be room for improvement by tweaking for the model further. And what we can say here, currently the model uses consecutive lag variables. However, consecutive lags might not always contain distinctive information. For example, the changes sensor values at lags 7, 6, and 8 might be minimal and not really informative to model, and higher lag variables might provide more distinctive information and improve model performance. However, adding higher lags will also result in more data being discarded due to nums introduced by shifting, so there is a trade-off to consider. And as engines approach failure, clear trends in sensor values become distinguishable between the single time steps, so constructive lags might be useful initially. A few variations will be tested to determine the best performing lags. So our last part here, finally, and let's look at this and what happens. Specific lags specifies which lag values to use for the time series, and X-ray interim and X-test interim intermediate data frames for training and testing data respectively. First, unnecessary columns are dropped, then remaining sensor data is scaled, made stationary, and specific lags are added. Finally, constants are added, and X-train and Y-train final training features and target variable. And again, a model fit part ordinary least squares regression model using the appropriate training data, and model fitted here fitting the all LS model to train data. By the way, I'm tired. and why head trained and why head and evaluate, and that part. Finally, let's look at our last outputs. What we can say here, the training RMSE and R squared to 20.74, indicating the average prediction error on the training data, and here indicating that 75% of the variance in the training data is explained by the model, and test set it indicates the average prediction, and same here. As a final, what we can say, the RMSE value of 21.14 is not bad, but can be slightly improved. The current model uses consecutive lag variables. However, adjacent lags may not necessarily contain distinctive information. For example, the changes in sensor values at lags 6, 7, and 8 might be minimal and thus not truly informative for the model. And when engines deteriorate and approach failure, there are clear trends in the sensors distinguishable between single time steps, and hence keeping the first few lags consecutive before increasing the time steps between lags is chosen. And trying a few variations showed that lags perform not best beat RMSE of 20.85, and these results are quite close to the previous SVR, I mean subaqueous regression, with an RMSE of 20.54. And that's all for our time series. Really, it is a long lesson. Thank you so much for your attention and listening. See you in the next lesson.